Solving systems of linear equations using matrices. So here we have a system of three equations with three variables. 2x plus 3y minus 4z equals 0, x minus 5z plus 2 equals 0, and x plus 2y minus 3z equals negative 2. And we want to start by writing the augmented matrix. But first, we need to make sure all of our equations are in standard form, and our second equation is not. So our first equation is fine, 2x plus 3y minus 4z equals 0. But for our second equation, we need to move our constant 2 to the right-hand side by subtracting it from both sides. And we end up with x minus 5z equals negative 2. And our third equation is in standard form, x plus 2y minus 3z equals negative 2. So now we're going to write the augmented matrix using the coefficients and the right-hand side constants. So in our first equation, we have 2 is the coefficient of x, 3 is the coefficient of y, negative 4 is the coefficient of z, and our right-hand side is 0. For our second equation, we have 1 is the coefficient of x. When we don't see a coefficient, it is an implied 1. We don't see a y, so it's like we have a 0y, and we need to put in the 0 placeholder for y in our matrix. Negative 5 is the coefficient of z, and our constant is negative 2. In our third equation, we'll have a 1 as a coefficient of our x, 2 is the coefficient of y, negative 3 is the coefficient of z, and our right-hand side constant is negative 2. So this is our augmented matrix for our system. Sometimes you put this little separator line to help make it more readable. It's not technically part of the matrix. Sometimes I use it, sometimes I don't. So with matrices, we have certain allowable row operations. What we are allowed to do is interchange or switch any two rows. We can replace a row by a non-zero multiple of that row. And we'll look at these when we do examples. And we can replace a row by the sum of that row and a constant non-zero multiple of some other row. What we are not allowed to do is divide. So we went through interchange, replace a row, and the two ways we can replace a row. So here, we are given a matrix, and it says write the system of equations corresponding to the augmented matrix, then perform the indicated row operations. So first, if we read through this matrix, we have a 3 by 4 matrix, 3 rows, 4 columns. We'll have 3 equations, 3 variables, and constants on our right-hand side. So this first row corresponds to the equation 1x minus 3y plus 3z equals negative 5. Our second row corresponds to negative 4x minus 5y minus 3z equals negative 5. And our third row corresponds to negative 3x minus 3y plus 4z equals 6. So that was our system of equations. Let's now do the row operations. Our first row will not change. So we're going to first look at our second row set of operations. And this rule says that row 2, or new row 2, will equal 4 times our row 1 plus our old row 2. So I'm going to write down, always looking in, going column by column from left to right, 4 times 1 plus negative 4. So 4 times the element in row 1, so 4 times negative 3 plus negative 5. 4 times 3 plus negative 3. And 4 times negative 5 plus negative 5. And then we will look at our third row. This rule says our new third row equals 3 times row 1 plus our old row 3. So for the first column, 3 times 1 plus negative 3. Second column is 3 times negative 3 plus negative 2. For our third column, 3 times 3 plus 4. And for our fourth column, 3 times negative 5 plus 6. So, simplifying, we get 0, negative 17, 9, negative 25, 0, negative 11, 13, and negative 9. So this is the resulting matrix after performing those two row operations. Okay, now let's write the system of equations corresponding to the augmented matrix shown here, and then perform the row operations indicated here as well. So the first row corresponds to the equation 1x minus 3y minus 4z equals negative 6. The second row corresponds to 6x minus 5y plus 6z equals negative 6. And our third row corresponds to negative x plus y plus 4z equals negative 6. So that's the system of equations. Now let's perform the indicated row operations. The first row is not changing, so I still have my 1, my negative 3, my negative 4, my negative 6. In the second row, this rule says that our new row 2 will equal negative 6 times row 1 plus row 2. So going through columns from left to right, we will do negative 6 times 1 plus 6, negative 6 times negative 3 plus negative 5, negative 6 times negative 4 plus 6, and negative 6 times negative 6 plus negative 6. The rule in our third row says that our new our new row 3 will equal row 1 plus our old row 3. So when we add together these rows, we'll get 1 plus negative 1, negative 3 plus 1, negative 4 plus 4, negative 6 plus 6. And now simplifying, that second row becomes 0, 13, 30, 30, and our third row becomes 0, negative 2, 0, 0. So this is our resulting matrix. Row echelon form is a matrix that is in this format. The key is we have ones on our diagonal starting from the upper left, and we have zeros below it. Reduced row echelon form would also have zeros above, but row echelon form is just zeros below. So the general steps in Gaussian elimination will be to first write the augmented matrix that represents the system, perform operations to get the entry 1 in row 1, column 1, perform row operations that leave the entry 1 in row 1, column 1 unchanged while causing zeros to appear below it in column 1. Then perform row operations to get the entry 1 in row 2, column 2, but leave the entries in columns to the left unchanged. Once a 1 is in its place, perform row operations to replace zeros below it. Then we'll repeat step 4 to get a 1 in the next row, but 1 column to the right. Continue until the bottom row or vertical bar is reached. Finally, The matrix that results is the row echelon form of the augmented matrix. Analyze the system of equations corresponding to it to solve the system. So we're going to go through these steps using an example. So I'm going to do a harder example. This is 4 equations, 4 variables. So we have coefficients in front of our w, our x, our y, our z, and row 1, which will be 1s. And so my first row in my augmented matrix will be 1, 1, 1, 1, 4. For my second row, I don't see a 0 w, but if we are missing a variable, we would fill that in, and we would put a 0 in the matrix. We will have a coefficient of -1 in front of our x and a 1 in front of our z. So that second row becomes 0, -1, 2, 1, 0. Our third row will have a coefficient of -1 in front of our w and a 1 in front of our z. So the second row will be -1, 2, 3, 1, 6. Our fourth row will have a coefficient of 1 for y, and our fourth row is 2, -2, 1, -2, -1. So this is our augmented matrix. We already have a 1 in the first row, first column, and we do have our first 0 beneath it, but we need to make this -1 a 0 and this 2 a 0. And there are different ways you can do this, but a way that will work every single time is to take the opposite of the number you're trying to change into a 0. So if we've got -1, the opposite of -1 is 1. Multiply that by the row that has a 1 in the column that we're dealing with, and add it to the original row. So our rule for row 3 will be, our new row 3 will be 1, because the opposite of -1 is 1. 1 times row 1, because that's where our 1 is, or just row 1, plus our old row 3. And for our fourth row, our new row 4 will be, the opposite of 2 is -2. -2 times row 1 plus our old row 4. Okay, so on the next slide, we will write the resulting matrix. So our first row doesn't change. We have 1, 1, 1, 1, 4. Our second row doesn't change. 0, -1, 2, 1, 0. And performing the row operations. So 1 plus -1 gives us 0. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 1 is 2. 4 plus 6 is 10. And for row 4, we're doing -2 times row 1 plus row 4. I'll do -2 times 1 plus 2, and that's 0. -2 times 1 plus -2, and that's -4. -2 times 1 plus 1, -1. -2 times 1 plus -2, -4. And -2 times 4 plus -1, -9. So this is our resulting matrix. So let's see where we are. We have our 1 in our first column, first row. We have 0s below it. So our next goal is to get a 1 in this position, the second row, second column. So to do that, we will multiply that row, and this is not the only way to do it, but it is a way that will work every time. I'm going to multiply that row by the reciprocal of the number I want to change into a 1. The reciprocal of -1 is -1 over 1, or -1. So essentially I'm multiplying row 2 by -1. So my new row 2 will be the opposite of my original row 2. My first row is not changing. My third row is not changing. My fourth row is not changing. 0 times negative 1 will stay 0. Negative 1 times negative 1 is 1. 2 times negative 1 is negative 2. 1 times negative 1 is negative 1. And 0 times negative 1 is 0. So this is our new resulting matrix. We have our 1, 0, 0, 0, and we have our 1 in the second row, second column, and we now need to turn this 3 into a 0 and the negative 4 into a 0. So our rule for row 3 will be the opposite of 3, negative 3. Negative 3 times row 2, because that's where we created the 1. So negative 3 times row 2 plus row 3. I don't want to use my row 1. I don't want to do negative 3 times row 1 plus row 3 because I will lose the 0 that's in my first column if I do that. So if I create a rule where I lose a 1 or a 0 that I created in a column to the left, rethink that rule because that's not going to work and you're going to have to go back and recreate those. For our fourth row, our rule, so I'm trying to turn a negative 4 into a 0. Opposite of negative 4 is 4. So 4 times row 2 plus the old row 4.